All right, today I will talk about Fourier analysis on finite groups. Recall that for any finite group G, LG, which is the space of all complex valued functions defined over G, can be made an algebra over the field of complex numbers with respect to pointwise addition and convolution, which is defined as follows: that for into functions phi1 and phi2 in LG, so phi1 star phi2x is so the value of the phi1 star phi2 at the point x is this one. So that is how the convolution is defined, and with respect to pointwise addition and this convolution, LG becomes an algebra over C. Note that this LG can also be made an algebra over C in another way. Uh, for in order to make it an algebra, we have to get an addition and a multiplication, right? So for addition, we can take the pointwise addition of functions as earlier, and for the multiplication, here we now consider pointwise multiplication of functions, which is defined like this: that for into functions phi1 and phi2, phi1 dot phi2 x at a point x of G, it is phi1 x times phi2 x. Since both of these are complex numbers, so the product actually makes sense. So this way we also can make LG an algebra over C. Well, in order to be technically precise, whenever I am saying an algebra over C, I just have to, I must mention the homomorphism from C to LG. So in this case, the homomorphism is uh, for every homomorphism is the following: that for every complex number alpha is being sent to the constant map alpha. Okay, whereas in the earlier case, the homomorphism from C to LG was the following: constant a scalar alpha is being mapped to alpha times E1, where E1 is the function that takes value 1 at the idea point at the identity of G and 0 elsewhere. So that's how we see that LG can be made an algebra over C in two ways. And I would like to say a few words about the second. That first of all, indeed, this is the most natural choice of products for LG, because any function, since G is a finite group, so if you just fix an ordering of the elements of G, then every function in LG can be actually really considered as a tuple of complex numbers. And when you have tuple of complex numbers, you want to define a product of two tuples to get another tuple. So the most natural choice is the coordinate wise product. Now once you translate this back to functions, you get exactly what we have done here. That is the pointwise multiplication. So indeed, this is the most natural choice of product on LG, whereas the convolution was highly non-intuitive. It came into the picture through a very particular map, namely this isomorphism between these two vector spaces, namely the isomorphism between two complex vector spaces given by each phi is being mapped to T phi. So if you can remember, so using this map, since this is actually an algebra over C, so using this isomorphism, we defined the convolution product on LG, so that now this isomorphism of vector spaces also becomes an isomorphism of algebras over C. Okay. Okay, so as I was saying, that we have now seen that this LG can be made an algebra over C in two ways. One is convolution and another way is pointwise multiplication. So it is very natural to ask if they are same or not. First of all, first of all, let me tell you that if you look at the definition, so here the product looks like this, and here the product looks like that. So from definition, uh, I mean, it is from definition, it seems like that this, I mean, these two ways will give us two different type of two different algebra structures on LG by appearance. Okay, because the product there is, I mean, if you look at their definition, uh, there is no natural way to see whether they have any relation between them or not. So from appearances, of course, these two algebras look different, but actually it is even more. Not only they are different by their appearances, their structure is also not same, because uh, this algebra, as I said, that when you this pointwise multiplication is pointwise multiplication, the algebra LG with respect to pointwise addition, pointwise multiplication is same as uh, having same as work dealing with a tuple of complex numbers. So actually this is isomorphic to that. Whereas we have already seen that this, with respect to the convolution, the group algebra is isomorphic to this, where these ni's are given by the following. As usual, we let rho wi rho I are all the inequivalent irreducible representations of G over C, and Ni is the dimension of Wi. So, as I said, that from the definition, they look different, but they are not only different by their appearances. Structurally, they are also different, because one is isomorphic to this, another is isomorphic to that, and they are clearly their structure. Their structure show that they are uh, totally different, unless and until each Ni is one, which is equivalent to saying G is abelian. So let me repeat what I just said. Unless G is abelian, so these two algebra structures on LG are not going to be isomorphic. Okay. Okay. Let's also yeah. So we have just I mean, to summarize what we have done so far, we have seen already we seen in one of the earlier lectures that LG with respect to this point convolution is an algebra which is isomorphic to that. Today we also we also we have also seen that with respect to pointers multiplication, it's also an algebra. We can make it an algebra as well in this way, and the two ways and the two ways in which we can make LG an algebra over C, namely the one for convolution and the one for pointers multiplications. So these two ways are giving us different algebraic structures. I mean, different algebra structures on LG. Okay, so let's focus on this. So we have already seen that with respect to convolution, this is isomorphic to this. Let's just recall how we arrived at this isomorphism. The isomorphism that you see here is actually the composition of two further isomorphisms. One is from LG to end R, where R is the right regular representation of G, and separately we have this isomorphism where end R is being decomposed into the direct sum of matrix algebras. So the composition of these two algebras, the composition of these two isomorphisms is the isomorphism that we obtained here in one of the earlier lectures. Okay, now what we are going to see is we will see a direct homoisomorphism from this algebra to the direct sum of matrix algebras, which is known as the Fourier transformation. This is highly interesting and important and interesting in its own right. And in fact, when G is abelian, that indeed connects these two ways of forming LG into an algebra over C. So let me just repeat what I said, that the algebra, the isomorphism here was early, that we got earlier, was the composition of this of two isomorphisms. But now we will see a very special isomorphism from here to here, namely the Fourier transformation, which is interesting in its own right, important. And not only that, if you remember a few minutes back, I said that we have two ways of making LG an algebra over C, and these ways are always giving me different algebra structures on LG. So when G is abelian, then the Fourier transformation also connects these two ways. And that is not somewhat surprising, because when G is abelian, so then this and these are actually same. So there should be some connection between them. There should be some, rather, I should say there should be some direct connection between them. So Fourier transform in the case for finite abelian groups, that does the job. Okay. So first we will study Fourier transformations for abelian groups. Once because that is in a sense of course that's in a sense simple, and that goes almost along the line of classical Fourier analysis on the real line. In fact, we will see the results like Fourier inversion, the analogs of the classical results like Fourier inversion theorem, Plancherel formula, Poisson summation formula in case of abelian, in case of finite abelian groups. And then afterwards we shall go for the general non-commutative finite groups, where things are rather more complicated. Okay, so so now we shall concentrate on finite abelian groups. For some motivation, let's start with the classical case of periodic functions on the set of integers. So the definition of a periodic function is the following, that it's a function with period n, where n is a natural number. Then f of x plus n should be f of x for every x for every integer x. Now from this definition, it is quite clear that if n is the period, then f of x plus n times m, where m is any integer, that's also fx, because this is just a repetition of this. And that actually shows that our function f is constant on every coset of the subgroup nz in Z. So let me just repeat. Let me just repeat. So from the definition of periodicity from definition of a periodic function with period m, we see that for any x, f of x plus mn is same as fx. So therefore, we get on every coset of the subgroup nz, the function f is constant. So once a function is coset, or one function is constant on every coset of nz, then the function can be realized as a function defined over z modulo nz. So we formalize that in the following way, that we define f bar as follows, that for a given function f, which has period n, F bar is defined as follows. F bar of x bar is f of x. You can check this is clearly well defined. And and now this map f goes to f bar for every f in for every periodic function f with period n establishes a 1-1-on-2 correspondence between the set of functions with period n and the set of functions and the set of functions defined over the finite abelian group z modulo nz, which is notationally this LZ modulo nz. So if man goes f going to f bar establishes and indeed establishes an isomorphism between them. So recall again, let's note how this is defined, or another way of saying that is the following, that f bar is defined in such f bar is the unique function that makes this diagram commutative. Okay. Okay. Now, since Z modulo nz is a finite abelian group of order n, so it has n distinct irreducible characters, right? Precise and because it's a finite abelian group of order n, as we have mentioned before. So, and this irreducible characters, n irreducible characters forms the an orthonormal basis of Z, L, Z modulo NZ. And in this case, this is exactly same as LZ modulo NZ, because since the group is abelian, so every function is class function. So this is this. Okay, so now, as I said, that this group has n distinct irreducible characters which form an orthonormal basis of the LZ modulo NZ. Let's first try to find out the characters. So in order to find the characters, it's easier to it is easy if we recall that yeah, in order to find out the characters of the group, it will be helpful uh, if we consider the subgroup of Sn, which is isomorphic to Z modulo nz, namely the nth group of nth roots of unity. And so this is isomorphic to that. And since this is a subgroup of S1, and for S1 we know that for every m integer m, so z goes to z to the power m is a continuous homomorphism from S1. So from that we immediately derive that for each m, that chi m of k bar is e to the power 2 pi I k m by n for every k is a homomorphism from Z modulo nz to S1 or equivalent, or in fact, or it's a since it's a homomorphism from here to here. Well, let me put it in this way: for finite abelian groups, since a homomorphism from the group to S1, the homomorphisms are precisely all the characters, because being a homomorphism from the group to S1 is same as being a character of irreducible representation. So from here, thus we have for every n, we get a character of the one-dimensional character of the group Z modulo nz. And from the definition, it's quite clear that all of them cannot be different. In fact, when m corresponds to 0 of 10 minus 1, these values of m, we get n distinct irreducible characters of the group Z modulo nz. And in fact, they are all because they have the correct number. Namely, since the group has order n, so it will have n distinct irreducible characters, and now we have n, so these must be all. In fact, no, these characters that establish, so the sending each m to the character chi m corresponding to that, in fact that establishes an isomorphism between z module and z and its dual group. So it's very easy to see, and so because that's easy to see in view of the definition of chi m. So I will skip it I will leave it to you to verify. And now let's say use that. Now let's use the fact that this chi m's form an orthonormal basis of the z module of z module and z. So therefore, if f bar is a function, for since if f bar well, let me just correct. So since for any given periodic function f bar is the function in z module and z, and since these phi m's form the orthonormal basis, so f bar admits an f bar can be written as a linear combination of them with these are the coefficients. This we can do because this chi m form an orthonormal basis of LZ module and Z. Now, like we will rewrite this equation. So f bar becomes 1 by n. So we just multiply each and every term by n and then divide everything by n. So this is the case. So now we will focus on this coefficient. So in this expression, now we'll focus on these coefficients. So for each k, this coefficient we easily see that the way. So from definition, this is just this, because chi k is e to the power 2 pi I mk. Now, since from the definition of f bar is just f of m. So this is easily seen to. So this is easily seen to be this. Okay. Now this expression actually looks familiar to us, and that indeed reminds us the classical definition of Fourier transformations on real line. So the only there in place of sum we have integrals. So keeping that analogy in mind, and also I mean the analogy, and also in case of Fourier analysis, we saw in case of Fourier analysis on R we see that periodic functions on R can be written as a linear combination of the of this trigonometric functions which are actually the characters there, but let's not get into that. So keeping in mind the scenario of writing a periodic function over R into a function of R with trigonometric functions, it is quite natural to call these things as the Fourier transform. Okay. Now for each f defined over z with period n, we make the formal definition. Now the Fourier transform is a function defined over z module n z, which is defined as follows. So I mean basically, as I said, this is what we want to say as the Fourier coefficients, keeping in mind the situation, the scenario over R. Let me again remind you, when R was a periodic continuous function, periodic and good enough function over the real line, then you can just take continuous function or L2 functions. Then since the trigonometric functions e to the power 2 pi n, they used to form an orthonormal basis of L2 of S1. So when we write the periodic function over R with respect to as a combination of these basis elements, so then the coefficients were in that expression the coefficients were the usual Fourier coefficients of the function, which were defined just like this, but there the sum was replaced by integrals, and necessary changes were there. So keeping that in mind, keeping that with that analogy, we are defining the Fourier transform of a function, of a periodic function over Z as follows. Okay, so you should, as I said, you should always keep in your mind the similarity of with the case over real line, and that actually, I mean, if that similarity, if you observe that, if once you observe that similarity, now then in view of that, this there should not be any problem to understand this definition for functions over Z. All right, so once we have defined this f k bar, f hat k bar, f hat is the Fourier transform of f. So once we make this definition, then in view of, and then this can be, so then we see that this is nothing but if, well, let me again show you. So the way the value of the Fourier transform is defined at the point k bar. So from the definition, it is clear that this is nothing but f hat k bar, and then the earlier expression is now rewritten as follows. Okay, because here we in the, yeah, so now this is as follows, because earlier it was just f hat m bar was the combination where we have multiplied each and every coefficient by n and divided everything by n, and once we multiply each and every coefficients, that become, from the definition of Fourier transform, the coefficient n times f bar in a product with chi k is just f hat k bar. So now, and on the left hand side, we had f bar m bar, f bar of m bar, which is same as fm from our definition of f bar. So thus this is what we get, and again this is also quite familiar to us because not exactly in this form, but we have seen similar things when sum was replaced by integrals replaced by integrals in the scenario of classical Fourier analysis on real line, and therefore like earlier, keeping the analogy, we will keep the analogy and call it the Fourier inversion theorem. So thus, like when we should again recall what we do in classical Fourier analysis over R, there our main objective was to write a good enough periodic function defined over R, right? That was our primary aim. Now when now in this case, when instead of R we are considering periodic functions over integers, which are same as the functions defined over Z modulo and Z, this is what we get. So f can be written as a combination with Fourier coefficients. So this is the version of Fourier inversion theorem. So okay. So thus keeping the analogy with the classical Fourier analysis on R, we have seen so we have seen its counterpart for periodic functions over Z. Okay, so for Z, this Fourier inversion, Fourier transform, Fourier inversion, we have now discussed. Now I will define them for general finite abelian groups. Okay, so let's do that. So let G be a finite abelian group. The set of all irreducible characters equivalently all homomorphisms from G to S1, which is denoted by G hat, is a group with respect to pointwise multiplication. This is what we call as the dual group of G. And I leave this to as an exercise to you, that G is isomorphic to G hat. We have already seen this when G was some Z modulo and Z, but now the exercise says it is true for any finite abelian group. And let me give you a hint to prove that. What you have to do is you have to decompose, because from the structure theorem for finite abelian groups, you know that G is the direct sum of such finite cyclic subgroups. And for finite cyclic subgroups, we know that they are isomorphic to their dual. Then you have to complete the argument by filling up the details that for each summand which are finite cyclic subgroups, since each summand is a finite cyclic subgroup which is isomorphic to its dual, so from that you have to prove that G is also isomorphic to its dual. So as I said, the hint is use the structure theorem for finite abelian groups. Okay. So for finite abelian groups, let's now define its Fourier transform. The Fourier transform of a finite abelian group G, let G be f be a function from G to C. The Fourier transform of f denoted by f hat is defined to be a function from G hat to C, which is defined as follows: that the value of f hat at a given point, points in G hat are the homomorphisms of from G to S1, so or equivalently the irreducible characters. It is basically this, and this is again by definition this. And this numbers are called the Fourier coefficients of the function f. So looking at this definition, you might raise a mild objection that why it has been defined as a function from G hat to C, whereas in case of G equal to Z modulo nz, f hat was defined as a function from Z mod nz. Actually, they are basically same in view of the following observation that which we have observed earlier as well, that for G equal to Z modulo nz, G hat is actually isomorphic to the group itself, and the isomorphism is sending a modulo class to the character corresponding to that modulo class. So what we have done here, what we had done earlier is we use the isomorphism of isomorphism between G hat and G when G was Z modulo and Z, and using that isomorphism we defined the Fourier transform. And you can compare that once you use this isomorphism and replace a character chi m by m, then precisely this is what you get. Precisely this is what you get. Okay, so since I'm running short of time, let's go ahead. So we have defined the Fourier transformation of a function defined over G to C. So from the definition, it is quite clear that if chi and phi theta are in G hat, then the value of the Fourier transform of chi at the point theta is precisely this, and that follows from the orthogonality relation of characters. And this shows that chi bar is indeed equals to order of G times E chi. So so regarding E chi, you should recall that when G is a finite group, G hat is also a finite group. So we can talk about LG hat as well, and there E chi is the a function defined over g hat is the function defined from g hat to c that takes the value 1 at the point chi, because chi is the point in g hat, and 0, it is taking the value 0 elsewhere. Okay, so with that, now it's very easy to see that for two characters chi and theta, so the inner product scaled by the factor 1 by order of g is just this, and this is this, and then it is an it is easy to see that e chi, the inner product of e chi e theta is precisely uh, uh, and so is precisely the inner product of chi theta divided by order of g, and since order of g is always getting multiplied here, so this equals to this. Okay, fine. Because here e chi e theta, if chi not equal to theta, then it is just 0, and if chi equal to theta, so this is e chi, that will be just inner product of that will be just 1 by so that will be just a scalar of order of g times 1, then we can just see that's in either case this is same as this. So this is clear, and therefore now this is clear, this is also clear. So thus for any two characters chi and theta, this is what I get. Now since this function, now since the bilinear, this is the inner product is a bilinear function, and this relation that this equals to this, both sides are bilinear, so therefore we can extend that this relation from the characters to arbitrary functions, because the characters, they form an orthonormal basis of the space of functions, and so therefore once we extend that, we get that for any two functions phi and psi, so this is exactly 1 by more inner product of phi and psi is same as the inner product of their Fourier transform scaled by a factor 1 by modulo g. And this is also, once we get that, that also reminds us quite well-known result from classical Fourier analysis, which is called the Plancherel formula. So this is the version of the Plancherel formula in the setup of finite abelian groups. Okay, now let's prove the Fourier inversion. So with that I will finish. Finish this video. So if f is a function in Lg, then f can be written like this, where f hat is the Fourier transform of f. Actually, this is very straightforward, because f admits the expression like this, and then you just apply the definition of Fourier transform, which is divided by 1 by order of g, and this is this. And now from the definition of Fourier transform, this has to be a f hat at the point chi. So with that, so that finishes the verification of the Fourier inversion theorem. So what it says that a function can be recaptured from its Fourier transformation. So from a function we considered we took its Fourier transformation. Now this says that the process is reversible. That is, knowing the Fourier transformation of the function, we can recapture the function itself in this way. Okay, I will stop now. So let me just summarize what we have done. Today, as I said, we will first study the Fourier analysis on finite abelian groups. So to begin with some motivation, we study what happens for the functions. We study what happens when the group is just a simple cyclic group of order n, because that is very much because functions defined over cyclic group of order n is same as the functions defined over z with period n. And in the classical Fourier analysis over R, we know that how to deal with good functions which are periodic over R. So for keeping that analogy in mind, keeping the analogy in mind, we defined Fourier. We defined Fourier transform function in that case, and with the transform we get the Fourier inversion theorem for periodic functions in Z. Now, so since for now we shall now sorry. So once we have understood for the very special group Z modulo and Z, then we developed the theory for a general abelian group. So we define Fourier inversion, Fourier transformations like this, and that gives us, without much difficulty, the Plancherel theorem and the Fourier inversion theorem as well. All right, thank you. So in the next video, we will talk about more fundamental results, more fundamental theorem of this study, which says that the Fourier transform that actually gives rise to isomorphism between the two algebras, LG with respect to convolution and LG hat with respect to pointers multiplication. Well, I have omitted that in both the cases the addition is just a pointers addition. So in the next lecture we'll see that f hat is not just a map which helps us to give f back. Indeed, that establishes an isomorphism between LG and LG hat. Okay, so I will stop here.